Okay, so this is your question that the sequence xn, where xn is equal to minus 1 or to the power n. We have to prove that this is not convergent. Okay, so let's do this one. Let us suppose that this sequence is convergent. Okay, then this sequence xn converges to a finite limit L. Okay, and therefore, for a given epsilon, let us suppose that this epsilon is some number value. Okay, let us suppose that epsilon is, you can take any value for this epsilon. You can just take it as, just try to take epsilon as a very small number. Okay, just take it as half, take it as 1/3, whatever. Okay, there exists a positive number n0 such that xn minus L is always less than half for all n greater than or equal to n0. You know this definition for a convergency. Now, in this case, sometimes n is even and sometimes n is odd. Okay, so if n is even, then if n is even, then this is 1 minus L is less than half. This implies your limit lies between 1 minus half is less than L less than 1 plus half, that is 3 by 2. Okay, so this is the range for limit. Limit lies between half and 3 by 2. And when n is odd, this is minus 1 minus L less than half. This implies minus and minus plus half is minus half less than, okay, wait, minus half, minus 3 by 2 less than L half plus 1. L is greater than 3 by 2. Okay, uh, minus half, minus 3 by 2 less than L less than, okay, minus half. Okay, whatever. So this is the range for limit when n is even, and this is the range for limit when n is odd. Okay, so that means there exists more than one limit for this sequence. Okay, which is contradiction, because limit is always unique. We have done this theorem. Hence, the sequence xn is not convergent, and it is also uh, what we say that this is non-convergent. The sequence is non-convergent. Okay, and it can also we can also verify that this sequence does not diverge to plus infinity and minus infinity. Actually, it is oscillatory sequence. Is that clear? So this is how you prove this sequence is not convergent. Okay, you can just go through that PDF file. You will find a lot of examples over there. Okay, now the important theorem is this one. You know what is a monotone sequence? That there are two kinds of monotonic sequence. One is monotone increasing and another one is monotonic decreasing. A monotone sequence, when bounded, converges, and a monotone sequence, when unbounded, properly diverges, and a monotonic sequence can never oscillate. Okay, you should remember this thing. Okay, so the first theorem is, if a sequence xn of real numbers is monotonic increasing, okay, and we write the abbreviation as mi, and bounded above. Okay, if a sequence xn is monotonic increasing and bounded above. Okay, what do you mean a bounded above? It has an upper bound. Okay, this theorem is very important. Okay, you should remember this thing. If a sequence xn is monotonic increasing and bounded above, then it converges to its exact upper bound. Then the sequence xn converges to its exact upper bound. Okay, or supremum of xn. It converges to supremum of xn. Remember, it converges to its exact upper bound. Is that clear? What is the, whatever be the upper bound, that sequence converges to its upper bound. Okay, let's prove this theorem. Okay, first of all, the sequence is monotonic increasing. What do you mean a monotonic increasing sequence? Then that is xn plus 1 is always greater than xn or greater than equal to xn. Okay, so this is monotonic increasing sequence. Then we can say that for all n belonging to n, xn is always greater than or equal to x1. X1 is the smallest one. Okay, so this implies this sequence xn is bounded below. Bounded below means it has a lower bound. Okay, and also from the given statement that it is bounded above, that means it has an upper bound. So this sequence is bounded. Okay, so the sequence xn is monotonic increasing, and so simply you can say that it is bounded because it is bounded below also, and according to the statement it is bounded above also. So hence the sequence is monotonic increasing and bounded. Okay, now again we know what is the least upper bound axiom. What is this LUB axiom? You know what is this? We have done in previous chapter that any sequence is bounded above, then supremum of xn exists in R. Okay, the LUB property says that xn is monotone and bounded above, then supremum of xn exists. That is supremum exists of that sequence. Okay, and let us suppose that m be the supremum of xn. Okay, also we can write this is an exact upper bound of xn. Okay, ub of xn. Supremum means it is the least upper bound, or you can also say that it is an exact upper bound. Now we prove that the sequence converges to this a. Okay. Okay, now what is the properties of this exact upper bound or supremum? For all n, there are two properties, you know that. Okay, that is the definition of an exact upper bound also. For all n belonging to n, xn is always less than or equal to m. You know that because m is the upper bound, so it is always greatest from all that members of xn. Okay, and another one, if you subtract minus epsilon from this m, then you will get at least one member from that sequence which is greater than that m minus epsilon. Yes or no? Okay, so there exists at least one member, say xp, which is greater than m minus at least one member if you subtract epsilon from that m. That's why it is least upper bound. Okay, there are some few numbers of upper bound, and from that upper bound you just take out the least one, that will be a supremum. Okay, that's why if you subtract minus epsilon from the least upper bound, you will get some members of that sequence which is greater than that m minus epsilon. Okay, so this was the definition of supremum. Okay, from this first we can write that xn is strictly less than m plus epsilon. Okay, for all if you add epsilon in m, then xn is strictly less than m plus epsilon. Okay, because you are increasing the value of that upper bound by adding epsilon. Again, since xp is greater than m minus epsilon, okay, suppose this is a sequence and over here there is xp. After xp you will get xp plus 1 and xp is always greater than xp plus 1 is always greater than xp because of monotonic increasing. And what is xp? Xp is also strictly greater than m minus epsilon, then all the members beginning from xp plus 1, they are all greater than m minus epsilon for p plus 1, p plus 2, dot, 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 dot. Okay, also p. Okay, since xp is also greater than m minus 1, then xp plus 1 also cannot be less than m minus 1. They are all greater than m minus 1. So what we got? We got xn less than m plus epsilon for all n. Okay, and another one, xn greater than m minus epsilon for all n greater than or equal to p. Okay, you can check in your book, the pdf file you can check, there is it is given, it is written less than, okay, but it is greater than. Okay, you can also rectify that one. Okay, so what we got is that xn is less than m plus epsilon for all n, and xn is greater than m minus epsilon for all n greater than or equal to p. So I can write m minus epsilon is less than xn less than m plus epsilon for all n greater than or equal to p. Okay, so since this is for all n, so this is also true for all n greater than or equal to p, and this is also true for all n greater than or equal to p. If you combine this both, then you will get m minus epsilon less than xn less than m plus epsilon for all n greater than or equal to p. So what does this mean? You can write this as xn minus m is less than epsilon for all n greater than equal to p. This implies limit n tends to infinity, xn always equals to. Okay, this was the definition of limit or convergence. Okay, that's why if a limit sequence is monotone increasing and bounded above, then the sequence always converges to its exact upper bound. Remember that. Okay, so there is another theorem. If a sequence xn of real numbers is monotonic decreasing and bounded below, remember that it is monotonic decreasing and bounded below, then it converges to its exact lower bound. Okay, so you prove yourself this second theorem. Okay, so in every class I'm giving you some assignments. Okay, so you just try to do everything. Okay, maybe someday I will ask all those things. I just want to check it out everything. Okay, so this is another theorem. So but if a sequence, there's another theorem, like if a sequence of real numbers is monotone increasing but not bounded above. Okay, that sequence is not bounded above, then it diverges to plus infinity. And similarly for monotonic decreasing, if a sequence xn of real numbers is monotonic decreasing and unbounded below, then it diverges to minus infinity. Okay, so you try to prove this theorem by yourself. Okay, it's easy, just check yourself. If you can't, then you can just ask me, right? So there is one example. We'll do that example now. The given sequence, you have to check the behavior of the sequence xn, where xn is given as 1 plus 1 by n. Behavior means you have to find the properties of the sequence, whether it is monotone increasing, monotone decreasing, whether it is bounded or not, or whether it is convergent or not. Okay, you have to check all those things. This is given. First we check whether it is monotone increasing or decreasing. Xn is given as 1 plus 1 by n all to the power n. If you expand this, so this is 1 plus n into 1 by n plus n into n minus 1 divided by 2 1 by n square plus n into n minus 1 into n minus 2 divided by factorial 3 1 by n cube plus dot 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 plus uh, n into n minus 1 up to 1 divided by factorial n into 1 by n to the power n. binomial expansion. So if you simplify it, this is 1 plus 1 plus, okay, so this is 1 by factorial 2. 2 is factorial actually. So n square, if you take out n square gets cancelled. So this is 1 minus 1 by n. Similarly, 1 by factorial 3, 1 minus 1 by n into 1 minus 2 by n. Okay, from here just take out n common, n cube gets cancelled, so the 1 minus 1 by n, 1 minus 2 by, and finally uh, the last term will be 1 by factorial n into 1 minus 1 by n into 1 minus 2 by n, 1 minus n minus 1 by n. Okay, so look, now this is your xn. Now what about xn plus 1? It is same, only 1 plus 1 plus 1 by factorial 2. This is 1 minus 1 by n plus 1 plus 1 by factorial 3, 1 minus 1 by n plus 1, 1 minus 2 by n plus 1, and the final last term will be, in place of n you will get simply n plus 1, 1 minus 1 by n plus 1 dot 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 1 minus n minus 1 will become n by n plus 1. So this is your xn plus 1. Now can you tell me which one is greater, xn or xn plus 1? Okay, so 1 minus 1 by n and 1 minus 1 by n plus 1. Which one is greater? 1 minus 1 by n or 1 minus 1 by n plus 1? Anyone? Which one is greater? No one. Okay, no one can tell which one is greater. So in this case, this is greater. That's why xn is less than xn plus 1. This implies because xn is monotonic increasing sequence. Okay, now next thing we have to prove that the sequence is bounded. Clearly x1 is equals to 2, which is less than all xn for all n. This implies 2 is lower bound. Okay, now we have to find the upper bound of this sequence xn. Now what if this sequence xn was given as 1 plus 1 plus 1 by factorial 2, 1 minus 1 by n plus 1 by factorial 3, 1 minus 1 by n and 1 minus 2 by n dot dot dot, and that last term. Okay, now if I write 1 plus 1, if I don't write this, I'll just write factorial 2, and I'll just write factorial 3, and similar I'll just write factorial n. So what should I write over here? Okay, look, mm, 1 minus 1 by n and 1, which one is greater? 1 is greater. So in place of 1 minus 1 by n, I have written over here 1. That's why this is always greater or equal, greater than or equals to. Is that clear? So finally, since it is greater than or equal to, so 1 plus 1 plus, in place of factorial 2, I'll just simply write 2. In place of factorial 3, I will write 2 square. Similarly, plus 1 by 2 to the power n minus 1. Now, factorial 3 is equals to 3 into 2 into 1. Okay, and 2 square is equals to 4. So 3 to the 6, 6. Okay, so this is always greater than 4. So 1 by 6 is always less than 1 by 4. That's why in place of 1 by 6, I have written 1 by 4. That's why again greater sign. Clear? So now this is a geometric series, and this can be written as 1 plus. So first term is 1, r is 1 by 2, so its sum is 1 minus 1 by 2 whole to the power n divided by 1 minus half, so which is equals to, this is less than equals to, if I simplify this whole thing, this is 3 minus 2 into 1 by 2 whole to the power n, that is xn is strictly less than 3. Therefore 2 less than equals to xn less than 3. This implies the sequence xn is bounded. Okay, since xn is monotone increasing and bounded, it is convergent, and the limit always lies between 2 less than equals to limit of xn less than equal to 3. The limit always lies between this. Okay, and we denote the limit of 1 plus 1 by n whole to the power n as n tends to infinity by the letter e. What is this e? E is the exponential, and the value of this limit e is 2.718281825, and it is an irrational number. Okay, so this example, why I'm trying to solve this example is that because this example is an example of a rational sequence having a rational limit. So this is a rational sequence having irrational limit. Okay, so your task is find an irrational okay, give an example of irrational sequence having a rational limit. So this is your task. So you have to give an example of an irrational sequence having a rational limit. Okay, let's go through the examples that is given in your that PDF file.